Yes, thank you. So first, I would like to say that I've been working as a motor designer for 4 years before joining the system simulation team for 4 years now, and just moved this week to system design leader position in Valeo. So I'm going to give you a view like more from the system point of view into the machine design, and how when I went from electrotechnical team to system team, I wanted to take with me the expertise that I had already and try to implement it on the system design view, from the system design view. So I will give you a small introduction about Valeo in case you don't know it. The context objective of this study, the powertrain optimization approach I am using, and then finish with summary and outlook. So in Valeo powertrain electrified mobility, so it's PEM, we are working mainly on electrifying mobility. So we want to be an active part of this movement to an electrified world in mobility and participate in providing a livable environment for everyone. So we are working on electrifying, starting small mobilities from small mobilities up to full electric family cars, passing through small electric vehicles, light, and different solutions of hybrid vehicles. We are using technologies in low voltage as well as in high voltage. So now when we are talking about the optimization of the machine itself, now it's not enough. Our customer is now want us to provide the full solution, the machine with the inverter and the gearbox, the whole e-axle. But when we consider the design of such a system, complex system, we are looking into having multiple components for sure. We are interested in these three, but we need to take into consideration the battery capacity as well. We have multiple design constraints concerning thermal, mechanical, and other constraints. We have multiple objectives. Yes, we want performance, but we don't want to pay a lot in order to stay competitive with the conventional cars. And then we need to respond to different design scenarios. So how can we take into consideration all these constraints? The idea is choosing to go to a multidisciplinary optimization. The idea now is that we receive requirements from the client. Usually we study these requirements and say, okay, so for this part of the system, we will take into consideration some requirements, and other we kind of distribute the requirements, the customer requirements to the subsystem requirements. So in general, it was the machine that is the interest, and the other components were a result. Their design space was a result. But now what we want to have is we take the requirements, we do a first study to define which are the requirements demanded from each part. So this is the multidisciplinary optimization approach that we want to adopt. The method that we chosen is the MWIA optimization methodology. I will take you through this method. So normally in the system, we have design variables. Design variables, we will apply different models, observation, physical models, and obtain the different observation variables that are of interest for us, such as an autonomy on cycle, a performance of the machine or the whole e-drive, the performance on the vehicle level, and of course we will have cost. And now we are taking into consideration as well the CO2 emissions of our product. So the problem in these observation variables is that they have different units and different ranges. And the idea is to apply some desirability functions that will describe our satisfaction of each observation variable and move them all into values between 0 and 1 that we are calling interpretation variables. So now we've saw the O, the observation, and the interpretation. Now we would like to aggregate all this into one optimization variable, that is the GDI, Global Desirability Index. And this is done via using aggregation functions. We can use, for example, simply having the minimum of all the targets, the observation, the interpretation variables, or having, for example, a weighted product. This way, if we know that the cost is more important, we can give it more weight compared to others. So now that we have this GDI, our optimization will aim at maximizing this GDI. So we'll apply some optimization algorithm that will look for the design variables that will maximize this GDI. This is the MWIA optimization methodology that we are applying. We can clearly see that we have two models in this case. We have a behavior model that is objective, and we have also a decision model that is dependent on the expert's opinion, on the customer needs, and it's the market trends as well. So this is subjective. Now let us take it into the electric powertrain point of view. So as I said, so we are interested in optimizing the e-drive, the gearbox, the machine, and the inverter. So we will have in the observation phase different models implemented here, as well as for the vehicle, if we are interested in calculating some performance on the vehicle level. We will use these models to evaluate the system requirements and then feed it back to our decisional model, the 3 steps of our decisional model. So the resulting platform that I worked, that was the result of this methodology, is the eDrive ED MWIA platform. It takes into, as an input, the requirements and constraints on the vehicle and gives a specification requirements on the level of components that will be handed over to experts to go through a more detailed optimization of these components. I'll give you some examples of the input data here. From the vehicle, we'll have the model of the vehicle, the mass, other characteristics depending on the vehicle. We have the vehicle requirements. So for example, range on different cycles, performance scenarios, for example, an acceleration or a gradability test. And then we have as well the eDrive cost and the carbon footprint of the product. Some examples of the vehicle constraints are battery capacity and the architecture. Do we want only one eDrive to be installed, or we have the possibility to have 2, for example. And then we need also to respect our own constraints, process constraints, targets concerning CO2 or other. For the observation model, we have different models of the eDrive. For the gearbox, we have, for example, single speed, twin speed models. For the machine models, we have parametric models, such as radial flux motor. And as well as we are working on having the axial flux motor models, in addition to our generic models that are built for the already existing Valeo machines. For the inverter as well, we have an inverter that is suitable for permanent magnet synchronous machine, for electrically excited synchronous machine, and we have also the generic models. Here I'm giving you an example of the machine model that we are using. This is one of them, but we have other as well. So this is a V-shaped magnet radial machine. So we can see here, So the idea is to be able to parameterize this machine well enough to have a good estimation of its performance when we have the calculation, but still not have a long calculation time when we have this model in the optimization loop. So here you can see that we have about 25 parameters, geometrical and electrical parameters. And the idea is to have 2D finite elements calculation to calculate the maps of the machine, as well as to have some tests, thermal tests, or like, for example, calculation of the short circuit current or other calculations that are needed for the estimation of the performance of the machine or the whole system. We also connected this model to a cost model that will estimate the mass and the cost of the machine, the resulting machine. So as you can guess, this model is built and calculated in GMAG, of course. Now, about the morphogenesis step, I can introduce it fast. So we've used the genetic algorithm. So you can find that we have the classical workflow of the genetic algorithm with in the first iteration, a random individuals generation. And if not the first, we have selection, crossover, and mutation. I won't get into details about it. But what we have added to this is an individual's validation. So why are we talking about individuals? So you know, in genetic algorithm, we have generations, and each generation has a number of individuals. So that's why I am mentioning individual here. An individual is a set of parameters of the machine and the inverter and the gearbox. So the idea, it's mainly the validation step, is very important for the machine, because it's not like if we generate like some parameters of the machine, we cannot guarantee that this machine is drawable, that is in fact represents a machine. So that's why we will need some pre-filtering step in order to validate that the generated individual by the algorithm is drawable. And also we can use this step to eliminate some like clearly not suitable solutions. For example, we can run some thermal tests, some calculations of the limits, and exclude already some individuals. And this will help converge much faster to the solution, the optimal solution. So here is the implementation that we have. So you can see, so what I did, I had a coupling between GMAG and MATLAB. Then we can imagine further how can we do things better. But this way, it's working quite well. The coupling via VBS files for as an input to GMAG and the CSV files from GMAG, it's working quite well. We are not facing any problems with this. So here, so we have already seen this is observation. We have the models. We have this coupling. If we have a machine parametric model, we will call GMAG to do the calculation and give us back the observation variables that are of interest. And then here I represented the design variables validation step that I told you about just before. So now I will show you a case study. So we have this system here. So we've chosen a mono ratio that we need to find this ratio. We've taken the same topologies that I showed you before. And then for the inverter, we only consider a limitation of current from the inverter. So we can see that like we are mainly optimizing the machine actually, but the machine with the suitable gearbox ratio. The objectives of this optimization are range on WLTC and NEDC cycles, and some performance scenarios in addition to the e-drive cost. So here when I'm saying the total e-drive cost, actually it's the machine in this case. It's only the machine. So we can see that we have more than 20 optimization parameter and more than 10 optimization criteria actually. And what I wanted in this study is to see the impact of the decision model on our optimization. Like if we take it from the beginning, we took into account what customer wants exactly. Not like, because we are accustomed to like giving a design and then the customer will challenge us to reduce cost or something. By choosing the decision model that is suitable to what the customer needs and that corresponds to the market trends, we can take it in the pre-design, these constraints. So now, the interpretation variables were aggregated into desirability optimization indexes, DOE. So here I explain. So we've taken all the objectives that are of the same nature. You can see here, we have the range, we have performance, and we aggregated them into desirability optimization indexes, 3 ones, so that we can have like a closer look at the performance of each type of objectives. And then we aggregate all of them into the JDE. Here, in order to go from here to here, we use the minimum function. So it's the worst result that will be limiting our DOE. And then for the GDI, we've chosen this formula. So it's a product, an average product, okay? So why average and not sum? Because some will, even if we have a case that is very bad, that for example, giving us 0 satisfaction, it will still be taken into account if another one is giving us a very good result. So this product will eliminate very bad solutions, like not acceptable solutions. And we've compared 2 cases. One that is cost-oriented, so we will put more weight on the cost, and one that is performance-oriented, that will have more weight on the performance. And we will look into the optimization results. So you can see here, so I represented all the objectives here on this spider plot. You can see how the result is completely different, actually. We have 2 different systems in 2 cases. We can see it from the performance is different as well as cost. And we can see here that if we compare, we have normalized everything. And we are comparing, we have the reference is the cost-oriented optimization. We compare to it. We can see by doing the performance-oriented optimization, we gain 3% in performance, 4% in range, but we have 5% more expensive system. So you can imagine, so this 5% is the machine itself. So you can imagine that behind this 5%, there is a modification, a quite big modification on the machine in order to get 5% in cost gain. And that's how I will come to the conclusion of my presentation. So it's the mobility electrification. It's coming with new challenges that now are really on the system level. Not only the machine, we need now to look into the design of the machine, but from a system point of view. So that's why this system approach is suitable for machine design. The multidisciplinary, multi-objective optimization approach will give us like new tools that will be very effective into having pre-designs of the machine and the whole system that will correspond much faster to the customer needs. and will avoid a lot of going back and forth between design, tests, and customer. The EDMWIA, just to give you like small recap about it, it's robust. When you define well your objectives, your constraints, it will always converge to the optimal solution. It is modular. We can easily replace some model of the machine with another one or another inverter. So it's very modular. We can add new models when we have. It is quite flexible, so we can do it. We can use it, as I said, for the pre-design phase, but we can imagine also use it for like refining some existing models. And the decision model is quite interesting to help us trace why did we do such a choice for the machine. Like someone will come and say, but why didn't you make it like you can make it less costly if you do this and this? I said, no, but according to our model, this choice was done because our customer needed this performance or this point of this scenario validated. So it will help us trace and explain how we did this technical choice. And further work is still ongoing. We are working all the time on how to enrich our library, improve the time of calculation, and have more design criteria taken into consideration. And that's it. Thank you for your attention, and please don't hesitate to ask questions.
Thank you very much, Mariam. Any question? Okay.
Thanks for your presentation. Myself, Ajit from Vitesco Technologies, and I have one question here. Could you advise to the engineer who has been working in the electrical machines with your simulation experience and this, the MOI status, how could you advise an electrical machine engineer that for a special application, what would be the best slot number and Paul ratio would be the selected for the application, and that would how it would be performance can be simulation or maybe optimized?
So using this approach of redesign, usually these parameters will be the main parameters that will be predefined by the optimization process, the system optimization process. You know, the output of this optimization will be the main parameters of the machine. And actually, we will not give like only one set of parameters and say, you need to do it this way, this number of poles, this number. We can give like few solutions, like let's say like a few acceptable solutions from a system point of view, and let the machine designer like look into more details. Because like, for example, in this optimization process, we cannot take into account exactly the impact of AC losses, for example. It's impossible. We are always in discussion with the electrotechnical team to give us some coefficients, some idea on how to estimate the AC losses, but we cannot do an exact calculation in the loop. So we will give these few solutions, but then the engineer himself will go further and tell us which one is completely bad solution from an electrotechnical point of view, or if it's not. I don't know if we can discuss also later if you.
Yeah, my name is Hackman, Vitesco Technology. I have a question regarding your cost information. What is included? Is only material costs or production costs? What's included?
We try to take as much as we can. Actually, we have a continuous discussion with marketing, with the process people, and we, from generic parts that we have already and that are already in the market, we take the data from this as an input for us and try to estimate if we are like really looking into like quite different power, let's say. we will discuss with the experts to try to evaluate the impact on the costs. But we will always be based on generic parts values, materials, process. Yeah, these two.
Because the reason for my question was the business case. So having a production line somewhere and trying to summarize different customers on one production line, have a new business case, have a scaling effect. So here you can find 10 up to 15%. And this is a kind of philosophy. Now, do I want to have a concrete optimization, or do I want to have a good business case? And yeah, this I think is a very important question for each.
Yes, for sure. Yes, for sure. For now, we are using these studies to define the need of the market, to propose generic parts that are suitable. So we have a lot of interaction with the customers, so we know a little bit what they are looking for, and we try to propose generic solutions. But then when we want to address a specific need will require more detailed optimization. Yeah.
Thank you for a very interesting presentation. Yeah, you mentioned the limitations from the inverter, and that was only the maximum current. But what about the maximum line voltage and the maximum fundamental frequency? How do you take that into account?
So we have detailed models of the inverter that are implemented also in the workflow, that we can calculate different voltages, losses, and different components of the inverter. But yes, for this case, we've had a generic part, and they gave us the limitation on the current. So for us, we've respected this limitation. Yeah, we didn't check the voltage, the output voltage. But we still have we have a limited voltage according to which we calculate the performance of the machine. We have this.
Okay, thank you. One last question. No, so I guess you need a coffee, right? Okay, so thank you, Mariam. Thank you very much for the presentation. Thank you for your questions. And let's have a coffee then. We will start again at 11.